Hello, Professor Chai. Today I'm going to be explaining to you how we do double displacement reactions. And for this activity, you're going to need to have your periodic table and your solubility chart, just so you can help follow along. So with this question, the main thing that it asks us to do is predict the products and write a balanced molecular, complete ionic, and net equation. And then it also says if no reaction, write no reaction. But I don't think we'll be needing to do that today. So the first thing that I like to do is I like to find out the charge of each element before I go ahead and balance it, or before I go ahead and try to predict the products. So for starts, we can see that calcium has a +2 charge, and then bromine has a -1 charge, but it makes sense because we have 2 bromine atoms, so it still balances out. And then potassium has a +1 charge, and SO4 has a -2 charge. And again, it balances out because potassium has that second atom to help it out. So these are all the charges. So when it comes to predicting products, I like to start with the inner. Let me use a different color. I like to use the inner with the outer. So in this case, we're going to start off with bromine and calcium. And it always helps to pair the positive first, then the negative. You always want to be positive before you're negative. So to write this out, we would have K, and I'm just kidding. We would have bromine and calcium. Okay, so a few things. I just totally messed up there. First of all, I called potassium calcium. That is not calcium, that is potassium. But yeah, it's actually supposed to be the potassium before the bromine. Like I said, the positive always goes before the negative. I completely messed up there. That is 100% incorrect. But the way we still handle the equation is basically the same. So it's not that much of the end of the world, so we'll still continue on. But again, just know that that is. And notice how we leave out the two, the two indicating that there are 2 atoms. We do this because it already has a balanced charge. So if we were to put this together, they both would have a +1 charge, so it ends up working out anyways. So we would just leave it at that. Okay, and then after that, we can move on to calcium and SO4, and we want to do the positive with the negative. So that makes CaSO4. Okay. And SO4 is the reason why we keep that together is because it's a polyatomic ion. That one is, I believe, that one is sulfate. So we keep that together. We treat it as one whole atom. All right. So now once we have our products predicted, we can go ahead and balance out our equation. So on this side, we have 1 calcium, 2 bromine, 2 potassium, and 1 sulfate. All right, and then on this side, we have 1 bromine, 1 potassium, 1 calcium, and 1 sulfate. So we can see that already this equation is not balanced, but that is an easy fix because we need one more bromine and 1 more calcium, and it just so happens that they already are together on the side, so that helps us out a little bit. So if I were to add a 2 in front of bromine and calcium, that would mean that there are 2 bromines and 2 calcium atoms, which makes this equation balanced. All right. And then the final step in writing out the balanced molecular equation is we have to figure out the different physical states of these electrons. Of these molecules. So for this part, this is where you have to pull out your solubility chart, and let's check bromine and calcium. So on the solubility chart I have, it says that halides, including bromine, is considered a soluble compound, and potassium also happens to be under that category as well. So automatically, this would make this solution aqueous. All right, and then for calcium, SO4, calcium sulfate, one of the first things that I notice is sulfate is considered a soluble compound, which would typically make this an aqueous solution. But one of the insoluble exceptions for sulfates is if it has a sulfate of Ag, Ca, Sr, Ba, Hg, and Pb. So because we have Ca, which is one of the insoluble exceptions, this would make this compound a solid. So that's really important. Don't forget to write in that information. All right. So this is going to be our complete balanced molecular equation. Now let's go on and do the complete ionic equation. So basically, with a complete ionic, you're basically just writing out exactly what this equation is saying, just broken down into little each individual pieces. So for example, we can start with calcium, and we know it's an aqueous solution with a +2 charge, and we leave it at that. And then we add bromine, which is also bromine 2, which is also an aqueous solution with a -1 charge, and that is our complete atom. And then we move on to the next one, and so on and so forth. All right, so I've already written out all of these atoms. Our final step is to put in the solid compounds. So the only ones that we're going to break up are going to be the aqueous solutions. We never break up the solid compound to help show us the reaction that occurred. So now I'm just going to write CaSO4, just how it is, and make sure to write down that this is a solid. And again, the reason why we do this complete ionic equation is so it helps us point out the differences between the products and the reactants, and we can see what type of reaction has occurred. So in this case, for the net ionic equation, we're basically just going to write out what changed. So on both sides, we can see that bromine stayed the same, and then potassium also stayed the same. So the only atoms that changed, or the only molecules that changed, is calcium sulfate and these atoms. So basically, we're going to write that down. So we write it down as calcium, aqueous, the +2 charge, plus sulfate with a -1 charge. -2 charge. And we also write down that it's an aqueous solution. And then we write down calcium sulfate as a solid. So now we can clearly identify the atoms that are reacting with each other and the atoms that made a difference, if that makes sense. So yeah, so this is how you do a double displacement reaction and write a balanced molecular, complete ionic, and net equation.